We've looked at the principles of beam behavior, and we've run through a quick example showing how those principles get resolved using some math. In these couple of kind of bonus examples, I'll go into greater detail, slow it down a little bit, and we'll design beams in both bending and shear, and then we'll also check for deflection. And we'll do this mostly in steel, just because that's the easiest. We have the best kind of data for it. Later on, we'll do, in a different video, we'll do one in timber and show how we back the section modulus figure that we need out of some simple formulas to calculate S. In this one, I want to just go through a simply supported distributed load on a steel beam. This is by far the most common and one of the simplest ones. It's one where we can use some formulas and have some shortcuts. So we'll get to some answers relatively quickly. Along the way, I'll explain each step so that it hopefully becomes second nature how we go about doing this and what the process is. No matter what the material, when we are designing beams, we'll go through this 7-step process. The first thing we'll do is look at the reactions that it takes to keep the beam in equilibrium. We've done a bunch of these. We don't need to do this mathematically if the beam is symmetrically loaded, but if there's anything that's off-center or anything weird, we'll go ahead and use the sum of moments around the left and right supports to figure out what the reactions need to be. We'll then either use formula from the moment diagram tables, or we'll draw the shear moment diagrams ourselves to find the maximum bending moment, Mmax, and the maximum shear, Vmax. We'll use the results of that and plug those into the flexure formula, this very simple M equals Fs formula, and we'll use the F allowable or the allowable stress in a material to figure out the section modulus that we need. Section modulus, remember, is a measure of the area, cross-sectional area of a beam, and that area's distance from the neutral axis. So it's a one-to-one measure of the effectiveness of a beam shape in resisting bending. We'll then take the section modulus that we need and we'll go find a shape that meets that or better. We'll either use beam tables, which we can do in steel, or we can work backwards to find a rectangular shape, or if you want a triangular or circular shape, but we'll stick with rectangles to figure out a geometry that will meet that S. And then we'll go through steps 1 through 4 again, including the self-weight of the beam, which will be a distributed load that will be the weight of the beam per linear foot times its length in feet. So we have to throw the dead load of the beam back into the equation, run the calculations again, and see if it works. If it does work in bending, then we'll go and we'll check in shear. We'll use the allowable stress of a material in shear, multiply that by the cross-sectional area, see if the beam's capacity is equal to or greater than the load that we're putting on it. And then finally, we'll use deflection formulas to calculate the beam's compliance with one of the two typical standards, either span over 240, which is a relatively loose, bouncy building, or span over 360, which is a little tighter. The tools that we have to use these, here is our chart of shear moment diagrams for simple loading conditions, point loads on the top, distributed loads on the bottom. And you see that in addition to showing us the shapes of the shear and moment diagrams, we have a number of equations here that let us shortcut this. So for example, the example we're going to do today, a distributed load on a simply supported beam. You see, hopefully by now, a familiar shear and moment diagram, a bow tie and frowny face. And you see too that we actually can shortcut this and we can use these equations to figure out maximum shear, maximum moment, and maximum deflection. That is only if we have a consistently distributed load and only if we have simple supports on the end, if everything is symmetrical. You can see that we have a number of common conditions, a cantilever with a distributed load here, with a point load here. Here, double cantilevers, we'll do one of those a little bit later. And you can see that those have fairly straightforward shear and moment equations to go with them as well. The other things in our toolbox are information about shapes, in particular steel shapes. Here we've got a chart that helps us pick a section by section modulus. Here the column showing the section modulus around the x-axis, that's the strong axis of a W-beam. You see we have here in both centimeters cubed and inches cubed. Those get greater as we go down, so we can just go down until we find the number that we need, read across, and that's going to be our first candidate for a beam shape. As we go down, you can see that shapes either get heavier or deeper as we get toward the bottom of the chart. And those are things that we will discuss about probably with our structural engineer. It's usually a trade-off between the depth of the beam and the weight of the beam. We can also go to this website, Engineering Toolbox, or to the American Institute of Steel Construction to get further information on a beam. And when we come around to deflection, we have to get some of this kind of deeper information, in particular the sectional area of the beam we're dealing with and the moment of inertia, which is how we measure or how we calculate deflection. So Engineering Toolbox is full of much more detailed information on wide flange beams, as is the American Institute of Steel Construction. Both of them have handy websites where you can get this information fairly quickly. And I'll have a link to that in the PDF of these slides. But we can also calculate the section modulus for simple shapes. So when we come around to timber construction, we will use this formula here, base times depth squared over 6, to find the section modulus of simple rectangular shapes. You can see we can also do that for triangles and circles, but 9 times out of 10 when we're dealing with timber especially, we'll be dealing with simple rectangles or built-up sections made of simple rectangles. And then finally, the material properties table gives us allowable stress in tension, compression, and shear, as well as modulus of elasticity. The allowable stress is going to be important when we're calculating for shear and moment in particular. You can see here the allowable working stress for steel in tension and compression. This is worth memorizing, 22,000 psi, and the allowable stress for steel in shear is 12,000 psi. Over here, modulus of elasticity, a measure you might remember of the stiffness of a material. Here you can see that the modulus of elasticity for steel is 29 million pounds per square inch, another figure worth memorizing. So between all of those, there are a few different places we have to go to get all the numbers we need, but they're all relatively handy, and there will be a PDF of all of these for each of the exercises that we do. We'll start with these, and that way they're easy to find as you're going through your own assignments. So in this example, we'll take a simply supported beam with a 1,400 pound per linear foot distributed load, and we will calculate reactions, we'll calculate the shear and moment. We will then look to see what section modulus we need in a beam shape, and we'll go to the steel tables to try to find one. Once we've found a shape that works, we'll check that for deflection and see whether we will know that the shape is strong enough. We'll see whether the shape is stiff enough to meet our criteria. So the first thing we do is we find the reactions. And in a complicated case, we would do the sum of the moments around the left and right supports. In this case, it's a symmetrically loaded beam. So we know that the collective weight of the distributed load is going to be shared equally between the two supports. Mathematically, we can write that as reaction right and reaction left are both equal to each other, and they'll be equal to 1/2 of W. Capital W is the total load that we're putting on the beam. Note that we have a distributed load though, so we actually have to calculate what the sum total of the distributed load is. We have 1,400 pounds per linear foot, and we have 40 linear feet of it. So not surprisingly, we multiply those two together, 1,400 pounds per linear foot times 40 feet. Feet will cancel each other out. We'll be left with a figure in pounds. And the sum total will be 56,000 pounds, and now we just have to divide that in 2 to get the reactions on both sides. So reaction left and reaction right are both going to be 28,000 pounds. The next step is to find the maximum shear in the beam. And to do this, we'll use the shear diagram, although we can wing it at this point. We know what the shear diagram is going to look like. We know where the maximum shear is going to be. But just to remind ourselves, the shear diagram will show the full 28,000 pound force. You can either think of it as pushing up, or you can think of that 28,000 pounds as the internal stress necessary to balance that 28,000 pounds. Every foot we go over to the right, the shear diagram comes down 1,400 pounds, because if we add 1,400 pounds, we have 1,400 pounds less to balance. Note the arrows are going in the opposite direction. So you can think of this as an infinite number of arrows, each one pushing down a little bit at a slope of 1,400 pounds for every foot we go over. Not surprisingly, that gives us an inflection point where the shear diagram crosses the zero line at the midpoint, and on the other side it gives us a shear stress, an internal shear stress of minus 28,000 pounds. So knowing that the maximum shear is 28,000 pounds, knowing that we have a bow tie shear diagram, we'll use this then to figure out the moment diagram. And remember that the value of the shear diagram equals the slope of the moment diagram. So here we start off with a very steep positive slope. We have a summit or a flat slope at the midspan, and then the slope gets steeper and steeper as we go toward the right edge. So this is going to be a curve, a positively curved shape, or a frowny face. And you can see here that a curve that matches it, steep at the beginning, shallowing out. An inflection point in the shear diagram means a summit or a valley in the moment diagram, and then a negative slope getting steeper and steeper and steeper until we come to the right end. The maximum moment will be at the inflection point, because when we change slope, it either means we're at a peak or a valley. Beam doesn't know the difference between a positive and negative moment. It only knows the absolute value of that. So we'll check wherever we have an inflection point, as shown by the shear diagram. And then remember that the value of the moment diagram will equal the area of the shear diagram up to that point. In other words, moment max will be the value of all of these little internal shears times each of their moment arm around that midpoint. So we want to find the area either under or over the shear diagram up to that point. We can go from either edge into the middle. It'll be the same. And our formula for the area of a triangle is 1/2 base times height, basic geometry. Our height is 28,000 pounds. That's the height of the shear diagram. Our base is going to be 20 feet, or 1/2 of the span, because the inflection point occurs at the midpoint. So we'll get a figure in foot-pounds, right? Feet times pounds, and that's what we're after. Moment is measured in torque, or foot-pounds. So running through that, 1/2 of maximum shear times 1/2 of the beam span, 1/2 times 28,000 pounds times 1/2 times 40, 14,000 pounds times 20 feet, or 280,000 foot-pounds. Now, that is our maximum moment without any dead load in the beam. We're going to have to come back and redo this calculation once we've made our first initial stab at what a beam shape might be. To do that, we're going to go to the beam tables. We need to find, first of all, the section modulus, and then we're going to go to the beam tables and find a shape that is greater than or equal to that required section modulus. So we'll use the flexure formula. Simple, M equals Fs, maximum moment allowed, equals the allowable stress of the material times whatever the section modulus is. The moment we've already calculated is going to be 280,000 foot-pounds, and we're in steel. So we can go back to our material tables, or we can just remember that the allowable stress of steel, of A36 steel, is 22,000 pounds per square inch. And then we get to multiply that by whatever we get for section modulus to build up to the resisting capacity in moments. We have to change foot-pounds into inch-pounds, remember, so that our units are consistent. So we throw in a factor of 12 there, and we can pull the 22,000 psi over. We divide both sides by that to get a clean S on the right-hand side. And what we get is S is 3.36 million inch-pounds divided by 22,000 psi. Note that the pounds will cancel out. Square inches will move to the top and multiply by that, and we'll get inches cubed. The required section modulus to carry that 280,000 foot-pounds in steel is going to be just under 153 cubic inches. Now we go to the beam table and we try to find a shape that has a section modulus greater than 152.7. If we come down here and look, we get bigger and bigger and bigger into the hundreds, and then right there, a W24 by 68 has a section modulus of 154 inches cubed. Now, that is greater than 152.7. It is just greater. And so we're going to be particularly keen to make sure that when we throw the weight of the beam itself into the equations, we're not overloading the beam's capacity. But taking just the live load into consideration, a W24 by 68 will work. It has a section modulus of 154, and we're trying to get a section modulus greater than 152.7. Section modulus there. Here's our beam. Our first attempt at a beam is the W24 by 68. Now we have to throw the weight of the beam back in, and for a W24 by 68, remember the nomenclature. The first number is depth, the second number is weight in pounds per linear foot. So instead of 1,400 pounds per linear foot, the real condition with the beam's own weight included is actually going to be 1,400 pounds per linear foot plus that 68 pounds per linear foot that the beam weighs, for a total of 1,468 pounds per linear foot. Now, the shape of the shear and moment diagram isn't going to change, but the values certainly will, because we're adding more load to the beam. So we need to run the numbers again. We will just find the moment using our M-max formula from the shear moment chart. And the maximum moment for a simply supported distributed loaded beam is WL over 8. And in this case, W now will be 1,468 pounds per linear foot times 40 feet. We'll multiply that by 40 feet again. Divide that by 8. Notice that we'll get a figure in foot-pounds. So 58,720 times 40 feet, 2,348,000 foot-pounds. We divide that by the constant 8. That just comes from the formula. It's given to us in the chart. And we end up with a maximum moment of just over 293,000 foot-pounds. So now we need to go back and we need to see if this combination of 68 pound per linear foot beam with its section modulus can carry its own dead weight plus the live load. Right? We have a new moment, we have a new section modulus. We need to rerun the flexure formula and see whether this beam can actually carry its own weight and the load. So we go back to M equals Fs, but this time we're hoping that this new moment is less than the strength of steel times the new section modulus. Moment now is 293,600 foot-pounds, 13,000 more than the original. Trying to see if that's less than or equal to 22,000 psi times 154 inches cubed. Remember, again, we have to convert to inch-pounds. So we end up with a moment that we're applying to the beam of just over 3.5 million inch-pounds. And in fact, that is not less than the capacity of the beam, which is only 3.39 inch-pounds. So because we're trying to load the beam to more than its capacity, this doesn't work. We're within the factor of safety, right? The beam is probably not going to fall down, but we do not let ourselves do this. We are above the allowable stress for steel, and therefore we've got to go back to the beam tables. And we either have to see if we can find a lighter shape, right, one that imparts less weight to the beam itself, or we've got to find a higher section modulus. So we'll go back to our beam tables, and here you can see here's the W24 by 68, and that had a section modulus of 154. Note that as we go down, we actually get much heavier beams, right? A W12 by 120, not quite twice the weight per linear foot, half of the depth. You can see that it's got a modestly higher section modulus, but there's no way that's going to work, right? What we can do is we can go down until we find a beam shape that's just a little bit heavier, but that has a much bigger section modulus. And what this means is either it's going to be much deeper, or the proportions of the flange to the web are going to be much greater, right? It's going to put more of its dead weight in places where it's doing the most good. And as we come down, we've got beams that weigh 86 pounds per linear foot, 83 pounds per linear foot. Oh, here we go. Here's one that's the same depth, W24 by 76 instead of a W24 by 68. So nominally, both of these are 2 feet deep. This one only weighs 8 pounds per linear foot more, but it has a section modulus that, as you can see, is 22 cubic inches greater. And if you run the percentages of that, we're adding much more section modulus than we are dead weight. And so we're kind of running ahead of ourselves here. And that looks like it might work. We could run all of these, but just to save time, let's go ahead and jump down the chart a little bit and run the numbers for a W24 by 76 and see if that gets us to a situation where we can actually carry the live load and the dead weight. So now, instead of 1,400 pounds per linear foot, we have 1,476 pounds per linear foot. We are adding the 76 pounds per linear foot of the beam itself. The section modulus of the new shape is 176 inches cubed. We get that from the beam charts. And we are just going to shortcut it, do the maximum moment as WL over 8. W now is going to be the revised distributed load, 1,476 pounds per linear foot. Span stays the same, 40 feet. We're timesing that by L, so we have 40 feet twice, once because this is telling us how much distributed load we have, this because it's part of the formula, and then 8 is just the constant, right? That comes to us from the formula, from the shear moment charts. So if we run that out, we end up with a new moment of 295,200 foot-pounds. So as we would expect, that's the highest moment figure we've dealt with yet, because it's the heaviest beam we've dealt with. But remember that our section modulus is getting much higher too. So that when we check the flexure formula, is the new moment that we're putting on it less than or equal to the capacity of the beam in bending, its strength times its section modulus? What we find is that 176 inches cubed is going to really help us. So the new moment, 295,000 foot-pounds plus a little bit, we're going to convert that to inch-pounds, remember. And over here on the right, this ends up being the capacity of the beam in bending, 3.8, almost 3.9 million inch-pounds. And when we do the calculation on the left, multiply that by 12 inches per feet, we get that we are imparting a moment to the beam of 3.5 million, just over, and we're allowed to impart a moment of 3.8 million. So in this case, we have a beam shape that actually does work in bending. This is the first of the 3 criteria that we're going to check. Just for giggles, compare that with the previous shape, maximum moment of 293,000 foot-pounds. And as you can see, we had a much, much lower section modulus. So we've gone up modestly in the weight that we're adding to the beam in the moment that implies, but we've gone up a great deal, 152 to 176 in terms of S, and therefore we now have a shape that works in bending. So we still need to check for shear and deflection with the new load, the weight of the beam, the dead weight of the beam, in addition to the live load. So first we'll check for shear, and to do this we'll take the load that we have, we'll plug it into the formulas that we have from the shear moment charts. The maximum shear in a distributed loaded beam with simple supports is just 1/2 of W, right? 1/2 of the total load. So the total load will be 1,476 pounds per foot times 40 feet. If we take half of that, we find that that is half of 59,040 or 29,520. We now need to see whether that is less than the allowable stress in shear. For steel, it's 12,000 times the cross-sectional area. So we find the cross-sectional area from our W-shaped tables. We go to Engineering Toolbox, or we go to AISC. We look up sectional area, and here we're looking at a W24 by 76. We find that the cross-sectional area of that is 22.4 square inches. So our formula looks like this. Here's the maximum shear that we're putting on the beam, 29,520 pounds. We need to see if that is less than the allowable stress in steel in shear, 12,000 psi, times the number of square inches that we have in the cross-section, 22.4. The allowable shear stress is 268,800 pounds. Shear stress we have is just over 10% of that, so we are totally fine. And this is what we would expect in a normal sized span with typical commercial or residential loading. We're almost always going to be governed by bending. So we're good. Last step is we want to find the deflection of our beam. We want to check to see whether it's within the parameters of either the span over 240 or span over 360. You'll always be told which. There'll be a specification that tells you the expectations for the kind of deflection or bounciness of the structure. In this case, we'll run both and see whether they meet one or the other or both of them. Now, here we've got to go back to those shear and moment tables, and in most cases we will have a formula that lets us figure out deflection. And notice that in this case, what makes a beam deflect more is more load or more span. Those are on the top side of the fraction. And what we have to resist that, not surprisingly, is the stiffness of the material, modulus of elasticity, 29 million for steel, and moment of inertia. Notice not section modulus, but that inches to the fourth figure that we dealt with briefly when we were looking at the derivation of the flexure formula. So we know all of these things. We can just plug and chug. The top of that is going to look like 5 is just a constant. The W we already figured when we were looking at shear, 59,040 pounds. And then the length L, since we're in inches, we have to convert it 40 feet times 12 inches to the foot. And notice that we're going to cube L. So deflection is very, very sensitive to length. 3 factors of length to every 1 factor of load. And then on the bottom, we have another constant, 384. This just comes from the formula. Modulus of elasticity of steel, 29 million pounds per square inch. And then the moment of inertia. And again, we can look this up in Engineering Toolbox. And I around X for W24 by 76 is 2,100 inches to the fourth. Notice the difference here between the moment of inertia when the beam is vertically oriented, this is around the x-axis, and the moment of inertia of a beam when it is horizontally loaded. So this is if you put the beam on its side, and you see here that you have much, much less, something like 5% of the resistance to deflection that you do when the beam is properly oriented. So we go ahead and run those, and not surprisingly, we get an absolutely ginormous number on the top, but not to worry because we also get a really ginormous number on the bottom. And when we divide the top by the bottom, we get a figure that is fairly believable. A 40-foot beam, 24 by 76, loaded with an additional 1,400 pounds per linear foot of live load, will deflect or sag about 1.4 inches in its middle. Now, that may seem like a lot, but we are allowed, remember, span over 240 or span over 360, depending. And in this case, if we run those numbers, a 40-foot beam divided by 240, we're allowed 2 inches of deflection. So if we're toward the bouncy end of the specification spectrum, we're absolutely fine. If we're toward the tighter end, and this would be for a Class A office or maybe an apartment building, something where people maybe are very sensitive to motion in the building, you find that we are just barely not okay, that the requirement there would be no more than 1 1/3 inches, and of course we're at 1.39. So we'd be very close, but here, depending on which deflection criteria we're picking, the beam either works or it doesn't work. And notice that all we can do in this case is go for a beam with a greater moment of inertia, right? We'd have to go back to the tables, this time to Engineering Toolbox, and we would probably be looking up at something like a W24 by 84. We'd have to go and run the numbers again to make sure it worked in bending. Pretty convinced it would work in shear, and that it looks like it would probably get us there in terms of deflection as well. Okay, we'll do 1 or 2 more of these videos where we look at examples of beam design. This is an important thing to understand just because it's something that will happen all the time in practice. Also because it deals with so many things, it's a good way to remind ourselves of all of the mechanics at work. We'll do a steel beam with double cantilevers, similar span but with cantilevered ends, and we'll look at what that does to the numbers. And then we'll also look at a rectangular timber beam, and we'll get some practice in kind of backing the section modulus out of the formulas that go into finding S for a rectangular shape.